We're now segueing into a little discussion as led by Ellen, maybe? No, as led by Chris. Chris, playing the role of Ellen.
Oh, you?
Whatever you like. Oh, okay. That's good.
Yes, so this, you have to imagine me as Ellen. I'm afraid I'm not a very good Ellen. She was tied up. So I don't want to keep you from the drink, so we have only a brief time. I came up with several questions that I thought we could talk about. And to start off with, why don't, I would like to suggest we talk about filaments. And we've heard about filaments on both large scales. Alyssa showed us today a map of Nessie, which goes on for 100 parsecs. And we also saw filaments on very small scales that we've seen in the H1 that are aligned with the magnetic field. So some questions are, what is the total amount of mass in the ISM in filaments? That is, are these things that we mainly just, that observers see because they're easy to see, or in fact is most of the mass of the ISM organized in filaments of some size? And then when you focus in on an individual filament, what is the structure of that filament? Is it held together by gravity? Is the size of it determined by ion neutral cross sections, for example? And I would like to throw open these questions, have people comment on anything they want about the filaments that we've heard about in the first 2 days. Don't all, well, go ahead.
So looking at the Planck images, I was struck by the fact that the incredible extent of these filaments. And I think there was someone asked the question of how deeply are we sampling with the Planck, because if you have a line of sight going all the way through the galaxy, I cannot believe that you would have the kind of structure that we see. I'm not sure what other people think about that, but it strikes me that we must be looking mostly at fairly local stuff.
Okay. Other comments? Yeah.
Yeah, I can answer that. It's worth pointing out that the Planck filaments and the H1 filaments are both relatively high latitude. So when we see the fibrous structure that Susan spoke about, that's very high, it's B of 90. So they're really, you don't have the confusion problem where there's many, many screens. You're basically looking at the wall of the local bubble. Same as what was spoken about by you today. Right, that's a single, most of the line of sight is nothing, and then you see some structure, and then there's not much else. Then there's an intermediate scale where the Planck folks have been looking at molecular clouds that are above the plane. When you get to the plane, all bets are off. I don't think anybody, I mean, there's things like Nessie, as you know, but there aren't things like we've been talking about with Planck and with Galp H1.
Yeah, the images, that's why I asked you the question yesterday. The images in Planck, you do not see that they're only at high latitude and then it disappears.
Yeah, it goes fairly close.
Well, no, but there is this fibrous structure appears over the whole sky. And so actually that's one of the questions a Planck expert might answer, which is whether there's anything in the data processing. Why is it that the Planck images look like Van Gogh paintings?
Yeah, I mean, yeah, exactly.
Yeah, there's a characteristic thickness. Does that have anything to do with the... Yeah.
Yeah, this is just visualization. It's just it's not physical structure. It's just a way to represent the angle of the polarization. And we use something like this brush technique, which is used in geophysics to represent winds on the ocean or winds in the atmosphere or waves on the currents in the oceans. It's exactly the same methods.
Okay, so if you just look at an intensity map, you're saying you would not see any of that. It's only when you include the polarization map and then it's a technique applied to show the orientation.
Correct.
Yeah, okay, well that's...
How far do you see with Planck?
You see everything. I mean,
Yeah, but that was a study focused very high light. Even less than the galactic plane. When you go towards the galactic plane, then you have the whole line of sight.
Yeah, okay, wait, let's get okay, let me give another mic. Maybe I should pick up this. Okay. Yeah, so next question.
I guess it was just related to this. So from what you were saying, the intensity map is if you didn't have those, the intensity map wouldn't show such structures. Right? And that's what's confusing us, I think, in the sense that we look at that polarization map and then we get confused by, and then we look at the intensity and we think that's what that structure is, and that it isn't that. So the other question is that then if you have the polarization angles like that, so that means that the polarization angles are coherent over those lengths, which means magnetic fields are coherent over those length scales. So we are transitioning, so what we see is actually an angle, so we need to know, obviously, what the length scales exactly is. So I don't know how to find that information. What's the length scales over which these magnetic fields are coherent?
So when you look, one of the confusing things then is when you look in the plane and you are, for the polarization map where you do see these stripes, you still get this very organized structure. And so that must be a structure at some characteristic distance that's dominating the orientation of the field, and then the rest of the fields are just canceling out.
We had this exact same discussion 2 years ago at the EPOS meeting in Ringberg, and I think it's become more clear in the last 2 years what's going on. I mean, correct me, Juan, if I'm wrong, but we are being essentially, yeah, it is an integral through everything, but we're being biased toward the stuff that's just a few hundred parsecs away in the plane and outside of the plane, everywhere, right? It's just the dust that's nearby. That's why the magnetic field orientation is so clearly associated with all the Gould's belt clouds and everything else, right? Is that not correct, Josh?
I'd say above the plane, 20 degrees or whatever, then yeah, it's the Gould belt clouds that we can get at. But then when you get towards the plane, I don't remember what the maximum opacity is, but it's in units of 10 to the minus lots. You can absolutely, every photon is getting to you from the other side of the galaxy. That's why very few of these studies are actually working in the actual plane. Not much is opaque. I could be wrong, but not much is opaque at 353 gigahertz. That just goes right through the galaxy. I mean, there's probably a few things, but not at 5 arc minute resolution.
I totally agree with that. Even in the galactic plane, you get all the photons, so you're not biased by the 200 or 300 parsecs in the galactic plane. We observe everything.
Yes, but
well, it's the cosecant law of yeah. So when you get to 15 degrees in latitude, you're dominated by what's local. But below that, it's
okay. Juan?
That's why in these relative orientation studies, we focus on the Gould belt clouds, which are a little bit off the plane. Otherwise, you'll be completely dominated by the galactic plane, and you wouldn't know if the morphology of the field that you're getting is just what is in the middle. The reason why it looks so homogeneous is basically because we just rotate by 90 degrees the polarization signal, and we call that the magnetic field. That is the reason why it looks so regular. It's just the projection. And we go to higher galactic latitudes, like Andrea did, or to intermediate to study the molecular clouds. But towards the galactic plane, we have all of the confusion. We're just seeing all of the galaxy.
Yeah, so the question is, we see all the galaxy in the plane, but you still see this very regular polarization signal. And so that suggests that is the polarization signal, as Chat suggested, being dominated by nearby gas or not?
Okay, I'm trying to, I guess I should know this, but I don't because I've forgotten. So the maps that we have of the starlight polarization, how far away are all of those stars? Right. So in some sense, that map looks like exactly like what the Planck maps look like. So in that sense, maybe that's, the fact that these two look so similar is, in a sense, that's the amount.
So that is an open question, Ram. So for example, when I did the study of the Gould belt clouds, we don't know exactly where is the signal coming from. Okay. So now we're comparing with the starlight, but there's not enough to those stars to actually make something like tomography of the field. See if the field is at 500 parsecs. We have an impression with the work that Luke Finfiner does of how much dust is along the line of sight. But exactly which is the component and how far those stars, we don't know. We have to two parsecs, one parsec.
Okay,
So Terry Jones in the early 90s did a study that's very relevant to this using near-infrared polarization. And he shows that in a polarization field with a constant and a turbulent component, you start out seeing the nearest side of the cloud, just because polarization is a vector, of course. It doesn't integrate along the line of sight like intensity does. Eventually, if the ordered component is really constant over the line of sight, eventually the turbulent one averages out, and you recover the single mode. So, you know, it depends a little bit on, I would say, about what the turbulent component or the non-regular component along the line of sight is, right? So if you're either having a very strong irregular component, you're seeing only nearby gas, because then otherwise the variations just cancel each other out, being vectors. Or if you have a very long line of sight, a very long column density with a regular component, you can recover much larger into that. But I think you have to make many more studies to answer the question whether Planck is seeing, you know, the surface skin of the polarization or a very, very deep constant component.
I just like what you said, because it brings a new dimension to this, because what usually is happening, we are considering polarization without relation to turbulence. And this is not true, because we have other techniques to study turbulence, and these scales that we are decorrelation scale for turbulence, they are the same for this polarization and magnetic field. So if we combine polarization with other techniques to study turbulence, I think we can have a much more significant progress.
Okay, Glennis?
If we could see that polarization map, my question would be easier for the people who haven't memorized it. Is that possible? You could put that on? But I can say the remark. So it seems to me that what you would expect as you look through the galactic disk is that, of course, we think the field is predominantly in the disk, and so since we're seeing that, that's sort of in many regions transverse to our line of sight. And so the fact that in the galactic plane you see it looking horizontal, great. So that seems like that makes quite a lot of sense. But what I find surprising is that you would get such strong structure, such well-defined structure, it seems, right? You would have sort of thought that it would get averaged out because you're integrating all through the whole disk. And so it seems like you need to write something like that where it looks like it's so structured. It seems like it must be something nearby. Isn't that sort of the case? That some one thing, maybe not nearby, but some one thing that's quite prominent has to be doing all of that little structure. Isn't
the opacity of dust in this wavelength is negligible. So all the photons are coming from the back of the galaxy. Even in polarization, and all the polarized photons are coming.
I'm not talking about opacity. I'm talking about emission. This is from emission, right? And so it's emitted. It's emitted where the dust is. If the dust is concentrated, wouldn't you agree? If the dust was concentrated in one spot, we would be seeing the magnetic field at that one spot.
Oh, that's very true.
If you look in the plane, then it's not concentrated nearby.
So
yes, and so the puzzle is why there's such sharp structure.
This is sharp. Would you?
Yes, really, you see little detailed wiggles, and it's so surprising that's not smeared out to me.
Okay, there's many things. There's the global galactic plane structure, the magnetic field is parallel to the galactic plane, and that's you said it's because we're looking at a spiral from the side, and the field, the magnetic field, is parallel to the spiral. So even if we're crossing several arms along the line of sight, the main component is parallel to the disk, and so that's what we're seeing, and it's not. It's weighted by density, that's true.
So what about the deviations? I agree, then it should be like that. But as Glennis is pointing out, there are deviations from the horizontal, and you would have thought they would have been averaged out.
Well, it depends. It depends what you cross along the line of sight. You're crossing different structures. The field is turbulent to some extent, so it's not totally ordered. There are variations due to turbulence, and it's creating those kinks.
And more lines of sight will pass through the same nearby turbulent cell, right? If you have a nearby turbulent cell, it has large angular separation, it will have its imprint. And then we'll have these small wiggles, perhaps from one nearby turbulent cell or from north polar spur, just because it's nearby, because many lines of sight pass through it. So there will be some averaging over a long line of sight.
That would be true only if you averaged over area, but pixel by pixel.
But pixel by pixel, we will have nearby structures which will be large in the sky and which will not be random in this sense. Because there is one such structure, not usually many.
Okay, that's fine. So let Josh's wishes to respond.
I'm just trying to remove all the hair from my head right now, if possible. I think one clarifying statement is that with starlight polarization, there's a significant opacity effect. And so the front screen affects the light in the back. So if you have a screen in the front of magnetic fields, it affects the light from the back. With emission from the dust, there's no screen effect. Okay, so we're all on the same page here that if you're looking towards, whatever, B of 10 or B of 0 and L of 10, so right through the galaxy, you're getting all of the light, and so you're getting all the Q and all the U, and everything adds up. Now, when you're going off the plane, many things you see, if you see a structure above the plane, that's a single cloud that is dominating the column density. So Gould belt clouds, all these molecular clouds that are 20 degrees off the disk. If you look, for instance, at Doug Finkbeiner's map, Eddie Schlafly and Greg Green's map, you see nothing, 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 a huge amount of extinction, and then nothing, nothing, nothing. And so the idea that it's correlated with that is not crazy, because you're not getting lots and lots of things along the line of sight until you get down to 10 degrees.
Okay, Enrique.
Okay, maybe this question will help, sort of guide some ideas. It's always puzzled me when you have an integration along a line of sight, like on the galactic plane. How relevant is the mean field if you are canceling out by averaging all the fluctuating component of the field? In fact, when I hear quotations to the values of the mean and the fluctuating or turbulent field, I systematically tend to hear that the fluctuating field is even stronger than the mean field. So after all, are we just seeing sort of like the weakest part of the field because the rest is canceling out, even though what's dynamically important may be the fluctuating components, at least on the plane?
Could you, Pat, wait, get the...
Yeah, when we study something like the ratio between the mean field and the fluctuating field, like what Andrea presented, he was doing it towards high galactic latitudes where you don't have this effect. Actually, if you check the first release of the Planck papers in polarization, we avoid that zone because we know exactly that. We're integrating many things along the line of sight, and we don't have any idea what would be the effect. Yeah, we see some features, but we're completely dominated by the magnetic field, by the dust in the galactic plane. So we always go a little bit off the plane to avoid this effect.
Okay, so
Okay.
let me just make one comment. This happens to be a particularly special direction because this is near the base of the North Polar Spur, and I think that the structure that Glennis was talking about that's 10 degrees off the plane that looks extremely ordered, I think that's related to the North Polar Spur and to the synchrotron emission, the magnetic field direction traced by the synchrotron emission.
Yeah, that's true.
Okay, one more, Alex, as our host.
Well, I should not explore this advantage. But I will be very short. Enrique, you see, we have not only emission polarization, we have also extinction polarization. And with extinction polarization, you can know where are your stars, and so there is no such an effect that we have, I think, really dominant fluctuating field.
Okay, so Blakesley has asked me to bring this to a close. So let's thank all our speakers again for today.